In this example, I'm going to demonstrate a few different forms of the energy intensity method in LEAP. So the first thing I am going to do is I'm going to make a mining sector to explain this. So again, I'm just going to, just like with the other method I did, first I'm going to add a new category. In this case, I'm going to call it mining. So I can work within that and it's then separating there. Now I have decided for this example that we are going to do two different methods or technologies that we use in mining. So the first is that we need to extract the material from our mine. So we will add, in this case, a technology with the energy intensity. We will call this extraction. And this will run on diesel. I should also mention these are totally fictive numbers, so they do not correspond to anything in the real world. It is just a method I need to share. Now, I will first want to establish my baseline, or my statistics. So I want to go into the current account scenario, which is where I define my statistics. You can see here I have activity level and final energy intensity as the two parameters I can adjust. Cost we save for later. So in this case, in terms of the mining, I can actually say how much material I think is going to be mined. In this case, I think we're gonna have 1 billion tons of material. So in this case, I'm just going to choose mass and say we're going to have metric tons. So this is our material mining. This is going to feed down to the further down the levels. Now in the extraction, how much are we going to do that? We are actually going to do the exact same. So we have to extract all of our mining. So instead of saying percent share here, we can say saturation, and it's 100. So that means of our 1 billion metric tons of mining materials that we work with, 100% of that is going to be used or have to be extracted. Now that's our activity. So that's, in this case, is 1 billion metric tons of materials we have to mine. And then what is the current final energy intensity? You can see the fuel is noted here. The general energy intensity for this is, as you can see, we have to define that as a unit of energy. We can define that to something else in gigajoule, but it is energy per the activity. In this case is metric tons. So in this case, we are going to use, for every a metric ton of material we are going to extract from the mine, we are going to use 100. And we can use a different unit here that makes a little more. We have a leap error. That's good. That was because I chose the wrong unit. Sometimes that happens, but in this case, we want to have something like I want an oil equivalent, so something like gallon, but I don't work in gallons. I'm just gonna find the right one. Okay. Tons of oil equivalent. No, I don't want to try to convert. And instead of, we are going to do 0.1 tons of oil equivalent per metric tons of extraction. And in this forecast, we are actually going to forecast that our mining will have to be deeper and more difficult to do. So that means we actually have an increase in our in the energy intensity of the sector. So This is for 2010. So in this case, I'm going to do an interpolation and say in 2030. This is annoying. I have to get that away. In 2030, I want that to be, comma, it's 0.1 now, we can see that. So we're going to double that to 0.2. And then in 2040, it's going to be 0.3. And this should be valid. So you can see the energy intensity actually rises here. So I don't know why this is as it is. It should be fine now. As we can see in our mining sector, it does also increase quite a lot our energy consumption. In this case, in the 1000 gigawatt hours, which is, if I'm not wrong, about the same as terawatt hours. So let's put it into that. So we are going, we are using about 1,100 terawatt hours in 2010 to do our mining. And then in 2040, that will actually increase to 3,400. And that is despite the fact that I didn't change anything in our activity, if I'm not wrong. So you can see I only have one basic activity. That means we're going to do 1 billion metric tons per year, which might also be a little much. So while we have that in the baseline, we can also put that into a growth. Actually, that's with a capital in the beginning. And I'm just going to say it's going to be minus 0.5%. I hate when it does that. So our activity, we're going to mine less, but the intensity is going to be bigger. So now if I calculate again, we can see that that actually we are increasing, but not quite as much. We only increased to about 3,000 now, compared to the 3,400 before. Despite our energy intensity was the same as before, but just because our activity now is less. Okay, other than just extracting from the mine, so what else can we do in the mine? So we can do some separation. And in this case, it will actually not let me do that because I have just a second. Now, as you can see, I've actually changed a little bit in my structure. I had to move a little bit things around. So now I made a subfolder just for the extraction, where we have the extraction of diesel. And I made another for mining itself. So I'm also going to move some of the activity levels. Should be now is actually being we have to move this, so we are going to have that 1 billion metric tons. Sometimes you do this a lot, and in this case I am going to delete this, and I am going to say no data. What happens when no data is that in this this is going to inherit from above. Oh, and this was 0. There has to be 1. So now it jumps this extraction layer because there's no data, and that is fully on purpose. So this should hopefully work well now. Yes, all should be fine. I should just check baseline. This is not super as I wanted to. We said that there was growth minus 0.5. that was actually 5, maybe. It was here that was missing. I apologize for that. Point. Good. Now this works again. And now we are going to make another aspect of our mining. So we are going to call this separation. But instead of having that as just as a category as seen here, instead we choose category with energy intensity. Note this useful energy analysis. We're not going to use it right now, but we're going to use that in a minute. So here we're going to call this separation. So we're going to separate the materials after we have extracted it from our mine. And now the reason why we now have a category with energy intensity is that we can specify the mining and the separation, and we can actually put in, instead of the node data here, we can say it has a saturation of 100 because, oops, see that's, if you see this weird curve we have here, and this is because I specified the 100 saturation in my baseline scenario, which is shown up here, instead of doing it in my current account scenario. So I'm just gonna get that away again, and then I'm gonna go to current accounts and say that it's 100% saturation. So now when I go back to my baseline, it is still flat, but at 100, as it should be here. And when I go to my energy intensity, you can see we don't really have anything, but if I go over to my category, we can add things under that. We can actually add technologies with energy intensity under that. Then they will share the same energy intensity, but there will be alternatives to how the energy intensity is fulfilled. So in this case, I'm just gonna call it separation is a diesel. I'm not sure it's gonna allow me to do that. I think it might. And I'm also gonna make another one called electricity, and I realize I can just say electricity, choose the fuel, and it will be named after that unless I specify something else. Good. Now I have the separation has the energy intensity. So per metric tons, we will actually say this is a lighter task. So we'll, yeah. It's because I'm using the scroll wheel, it does not like that. We'll put that into kilowatt hours. That's fine. It cannot convert that, and it shouldn't. And we are gonna use per metric tons, we are gonna use 80 kilowatt hours in this case. And I am doing that in the wrong scenario again. That happens a lot. Gonna go back, 80 kilowatt hours. And we are gonna get better at that. So we are making sure that in the future, I don't like the window, in 2020, we are going, instead of using 80, we are only going to use 60. And in 2040, actually, I regret that. We're not going to use interp, we're going to use smooth. And away with that again. So again, 2020, we are going to use, we are having that as a 60. And by 2040, it's going to be 40 because learning gets more difficult there. This should do it though. Good, so now you can see that we have an overall smooth line between our 3 points. And we define our points in the beginning and in 2020 and in 2040. And that cannot be seen had we done this instead with interp. We're just going to remove this and write interp. Then you can see it's a lot more, we have a jagged edge, so to speak, here. But in this case, we would like it to be smooth because learning is a smooth thing. So we're going to do it like this. Good. But now they have the same energy intensity, and we can say what kind of share is there between these fuels or these technologies. So today they are, I'm going to say remainder 100 because this is a percentage value. That means I never have to adjust the diesel. I only have to adjust electricity because that's where I want to base my policy. In this case, in the current scenario, on the current accounts, it's 0. Good. That means it's 100% diesel. Then if I choose my baseline, then actually we're going to have a big separation thing coming online. So we're going to use a step. So, and that's going to be in 2024. We are then suddenly going to have 50% of our separation done by electricity. And it's going to be in one fell swoop, and that's going to happen. So you can see that changed quite a lot. Now we should actually have an energy forecast for this as well. First, I want to really quick see that if my extraction worked, and that worked fine, that's good. And my separation, you can see now suddenly we actually have a falling energy intensity or an energy demand. That is because we have a negative growth in our activity because we're getting less mined, but we also have a fallen energy intensity, which means we're going to save energy over time. But as you can see here in 2024, suddenly half of our demand actually is converted from diesel to electric, because now we're having some new unit online, and that's going to follow. Even though it's falling, it should now be, it still is half. Of course, if this unit will come online, it would actually be a larger percentage. So that's a bit of a thing that can be discussed in this with this method. Now we want to change that actually a little bit, because diesel and electricity is not the same thing. So we're going to say here, going to say properties. What we didn't do before, we're going to do now, and say useful energy analysis. And we can also say final energy intensities and current accounts. Now, since you have two technologies where one is 100% in current accounts, and we're not going to change that, this doesn't actually matter, but for this case, we actually put it on. And that means your statistics in terms of how you input your data can be slightly different, because it will still be final energy intensity. Now, the difference is now in our current account, as you can see, we still have activity level, final intensity, but then we also have efficiency, and that cannot be adjusted. But as soon as we get into the baseline, that is something we can now adjust. So I'm going to say that the efficiency of our diesel generator is actually around 30%. Actually, I need to do that in my, I still need to do that in the current accounts. So that's going to be diesel, it's going to be 30%. And in this case, the efficiency for doing it with electricity, since it's just an electric motor, and that is 96% efficient or something like that, we're going to put that at 96%. Now, of course, if we do that, we should also change our energy intensity, and the difference between a useful energy intensity and the final energy intensity. Now we don't have to account for the inefficiency of the, in this case, diesel or electric motor. So we can just take the pure method, which in this case we can call it to be about 40. So the real life is 40, but now we also add the inefficiency or efficiency on top. The fuel share in this case, not touching it. Oh, actually it did change something for us. I am sorry, why didn't it do that? So in this case, we are gonna again Haha. And that's because it's a different method now. So the activity is done on both, it's done for the separation, which is 100% saturation. And now we have to define it for each of these because they don't have the same, the process has a energy intensity, the motors does not. So what we said here in the current account, we just still have, we don't have this because it works with the final. But in the future, the activity level here, and these are given as a percentage share. So here I'm gonna call it again, remainder 100. And then here I'm gonna say we should call it was a step. So step 2024, comma, and that was 50%. So that's coming online now. So that should change our situation quite a lot, because I now added the efficiency specifically for the two motor types. So let's calculate. And let's go and see in separation. You can see we have a falling method, or the falling energy demand. That's just because the growth is -1. That's or -0.5%. That's mostly it. And then also the general efficiency. I think we had an efficiency improvement for the diesel as well. And you can see suddenly, whoops, because the efficiency of the electric motor is so much better than the diesel separator. Suddenly our total energy demand, while this comes online, falls quite a lot. And this is actually quite a real situation if you suddenly have a system coming online that's way more efficient and then takes about half of your consumption demand, I mean the activity demand, then it has a big effect that is not that obvious necessarily for the energy demand. But that is what we see here. So that is what I wanted to show with the energy intensity. And as you can see, it's quite useful in a number of different situations.